wireless LAN controller must also authenticate each other with digital certificates. An X.509 certificate is pre-installed in each device when it's purchased. By using certificates behind the scene, every device is properly authenticated before becoming part of the wireless network. This process helps assure that no rogue non-CAPWAP AP can be introduced into the network. The CAPWAP tunneling allows the LAP and wireless LAN controller to be separated geographically and logically. It also breaks the dependence on layer 2 connectivity between them. For example, in this figure, this figure uses shaded areas to show the extent of VLAN 100. Notice that how VLAN 100 exists at the wireless LAN controller and in the air as SSID 100 near the wireless clients, but not in between for example, LAP and the wireless LAN controller. Instead, traffic is to and from client associated with SSID 100 is transported across the network infrastructure encapsulated inside the CAPWAP data tunnel. The tunnel exists between the IP address of the wireless LAN controller and the IP address of the LAP, which allows all of the tunneled packets to be routed at layer 3. Actually here, this is the IP address of the lightweight access point or LAP, and this is the IP address of the wireless LAN controller, and now we have a CAPWAP tunnel. Because of that, we can encapsulate the data received from wireless client with SSID 100 to the wireless LAN controller, and after that, the wireless LAN controller, after de-encapsulating, can tag the frames with tag, for example, 100 and forward them to the wired network. Also, notice how the LAP is known by only a single IP address, 10.10.10.10. Because the LAP sits on the access layer where its CAPWAP tunnels terminate, it can use one IP address for both management and tunneling. No trunk link is needed between all of the VLANs it supports are encapsulated and tunneled. As the wireless network grows, the wireless LAN controller simply builds more CAPWAP tunnels to reach more APs. This figure depicts a network with 4 LAPs. Each LAP has a control and a data tunnel back to the centralized wireless LAN controller. SSID 100 can exist on every AP, and VLAN 100 can reach every AP through the networks of tunnels. Once CAPWAP tunnels are built from a wireless LAN controller to one or more lightweight APs, the wireless LAN controller can begin offering a variety of additional functions. Think of the puzzles and shortcomings that were discussed in the previous videos for the traditional autonomous WLAN architecture as you learn about them. And now let me to explain some of the features that wireless LAN controller or the split MAC architecture can provide for us. First, dynamic channel assignment. The wireless LAN controller can automatically choose and configure the RF channel used by each LAP based on other active access points in the area. This is the dynamic channel assignment or DCA. The next feature is transmit power optimization. The wireless LAN controller can automatically set the transmit power of each LAP based on the coverage area needed. Then we have the feature of self-healing wireless coverage. If an LAP radio dies, the coverage hole can be healed by turning up the transmit power of surrounding LAPs automatically. After that, flexible client roaming. Clients can roam between LAPs at either layer 2 or layer 3 with very fast roaming times. And then we have the benefit of the dynamic client load balancing. If 2 or more LAPs are positioned to cover the same geographic area, the wireless LAN controller can associate client with the least used LAP. This distributes the client load across the LAPs. After that, we have the feature of RF monitoring. The wireless LAN controller manages each LAP so that it scans channels to monitor the RF usage. By listening to a channel, the wireless LAN controller can remotely gather information about RF interference, noise, signals from neighboring LAPs, and signals from rogue APs or an ad hoc clients. Also, we have the feature of security management. The wireless LAN controller can authenticate client from a central device and can require wireless clients to obtain an IP address from a trusted DHCP server before allowing them to associate and access the WLAN. And finally, wireless intrusion protection system, leveraging its central location